new 5G band below 1 gigahertz is one is 700 megahertz, and other band in our country is 3.3 to 3.6 gigahertz, sub 6 gigahertz band. In the case of millimeter wave band, we have 24.25 to 29.5 gigahertz band and 37 to 43.5 gigahertz licensed new 5G band in India. And for 6G, so commercial deployment is expected by 2030. Wireless radio conference 2027. So here the 6G aspects will be finalized. 6G study is going on. It will be completed by 2026. Aspects will be finalized by 2028, and commercial deployment we are expecting by 2030. Features in 6G wireless communication. These are the features. Sustainability. It should support sustainable network of networks. So virtual slicing, connecting intelligence, trustworthiness, extreme experience, ubiquitous communication. Okay, and the technology that it will use. So local spectrum licensing, spectrum sharing, infrastructure sharing, the 6G network will use this technology. And intelligent automated management supported by mobile edge computing, AI, and blockchain technologies. So 100 gigahertz to 3 terahertz. So 0.1 terahertz to 3 terahertz, these are promising bands for next generation 6G wireless communication system. Expected data rate is 1 Tbps. So for realizing 6G wireless communication, first I will discuss terahertz components. And then I will come to millimeter wave and microwave components. Yes. So for terahertz component, first component I will discuss today is basically tunable dielectric resonator antenna for terahertz application. It is quad band also, it is circularly polarized also, and it is tunable. So quad band plus circular polarization and graphene based tunable DRA for terahertz. So you are seeing the structure of the terahertz DRA, top view and side view of the terahertz antenna. We have used basically cylindrical dielectric resonator, this one. So pink color cylindrical dielectric resonator, dimension is indicated. It can be designed in CST Design Studio. Height is H1 and diameter is shown here 8. And this is basically the top view. And this yellow color is basically the ground plane made of copper. You can take silver also. For the substrate, SiO2 material is used, so it is available in CST library. Silicon dioxide. And this is a feed configuration. Aperture coupled feed configuration. So here my microstrip feed line thickness is WF, length is L, and left and right arm is also shown here. And this is basically the aperture coupled feed. So circular ring is there with 2 arms. So here is basically the top view, and this is the feed configuration, multi-layer structure. Okay, so we'll study. This is the final design with 2 arms, left and right arm. And this is microstrip feed line, and 2 patches are also here, left and right patch. So what is the result of this structure after simulation in CST? Since this is a cylindrical dielectric resonator antenna, so what modes will propagate, that also we have to see at terahertz frequency. So terahertz resonance frequency, in the case of CDRA, the dominant mode, the fundamental mode is HEM11 delta. This is the fundamental mode of propagation. in this type of a structure, cylindrical dielectric resonator structure. And the frequency of this fundamental mode is given by this equation. And here the result is shown here, S11 versus the frequency. So at what frequency this antenna is radiating, that we can see in this result. So right arm, left arm, circular slot without any arm and two arms. So this is basically we have done the systematic study. So first circular ring is taken, then left arm, right arm and the two arms. And we have seen the effect of this kind of feed, aperture coupled feed. So you can see the result here, circular slot only, black color, this result, without any left right arm. So if this structure we choose, what will be the result? So we are basically seeing we are getting 1 and 2 band. Second band is also just it is equal to 10 dB. And in the second case, right arm S11 red color. So right arm we are seeing 1 band and second band, 2 band. And then S11 left arm blue color. So again dual band. Final structure circular ring, circular slot with 2 arms. So in this case, we are getting tri-band, 3 band. So it is still not quad band. So we will see quad band result also with 2 arms. Now we are getting triple band. So pink color 1, 2 and 3 band we are getting tri-band response. This antenna is radiating at triple band concurrently. And the dimensions of the circuit, because for designing you need the dimensions, so that is also indicated. Using transient analysis, you can decide the dimension also, and then you have to optimize for tuning. So triple band we are getting, it is resonating at 8.12 terahertz. This is S11 minus 16 dB. Then next is 11.38 terahertz. S11 is minus 23.8 dB and 15.29 terahertz. S11 is minus 26 dB. So 3 terahertz band it is radiating at, and this is showing basically the 2D, two-dimensional far field polar radiation plot. So as per this plot, the gain is 4.73 dBi at first band, I mean 8.12, center frequency of first band, 8.12 terahertz. Then for the second frequency, 11.38 terahertz, the gain is 3.15 dBi, 11.38, and for 15.29 terahertz, the gain is 7.08 dBi. So that also you can see CST. And this is main lobe direction. At first frequency, second resonance frequency, and third frequency, 4 degree, 11 degree, and 0 degree main lobe direction. Now the bandwidth, it is radiating at triple band. So what is the bandwidth? So at first band, it is, this is the first band. It is centered at 8.12 terahertz. So it is from 7.93 to 8.48 terahertz. And second band is centered at 11.38 terahertz. So the bandwidth, I am talking about the impedance bandwidth. So impedance 10 dB bandwidth is equal to 11.74 to 10.87 terahertz. So it is 7.6% narrow band. And then the third band is from center frequency is basically 15.29 terahertz, bandwidth is 14.5 to 16.47 terahertz. So these are the results in terms of the antenna reflection coefficient and 2D polar plot, antenna gain, antenna main lobe direction, and antenna bandwidth. Okay, so after this, and the cylindrical dielectric material. So this is made of silicon. It is made of silicon. Epsilon r is equal to 11.9, and mu r is 1. Conductivity of silicon 0.00025 Siemens per meter at 300 Kelvin. So you can choose directly silicon material in CST Designer Studio. It is there in the library. So CDR material is silicon, substrate is silica. Now next is for terahertz communication. If we use this antenna, what will be the which mode it is propagating? What will be the electric and magnetic fields? So at different frequency, 8.12 terahertz, 11.38 terahertz, and 15.29 terahertz. What is the mode? What mode it is propagating? So at first frequency, lower band, 8.12 terahertz, electric field distribution is shown here. So electric field and magnetic field distribution is shown here. So from seeing this electric field distribution, you can tell which mode is propagating. Now for knowing, okay, what is the electric field configuration and magnetic field configuration for certain mode, any mode, HEM11 delta mode, transverse electric mode, transverse magnetic mode, HEM12 delta mode, HEM21 delta mode. So TE01 delta mode, TM01 delta mode. So what is the electric field configuration corresponding to that mode for cylindrical dielectric resonator antenna, CDRA, DRA. So cylindrical dielectric resonator, yes, dielectric resonator antenna. So for knowing what mode is propagating for this kind of a structure, you can refer two books by Luck and Liang, DRA designed by Luck and Liang, and other is Aldo Petosa, DRA designed by Aldo Petosa. So there it is given for cylindrical dielectric resonator antenna. What is the electric and magnetic field configuration for HEM11 delta mode, for TM01 delta mode, for T01 delta, for different modes? So now we are obtaining, this is our result, we are obtaining this kind of electric field configuration at 8.12 terahertz in CST Designer Studio. It resembles like this electric field vector orientation resembles like HEM11 delta mode. So that means at 8.12 terahertz resonance frequency, HEM11 delta mode is propagated. Now next, second frequency is 11.38 terahertz. This is the field configuration shown here. By seeing this kind of electric field, rotating electric field distribution, so this orientation resembles like transverse magnetic mode. This is basically TM01 delta mode. TM01 delta mode configuration. So at 11.38 terahertz, we are calling that okay, TM01 delta mode is propagated. At third resonance frequency, 15.2 terahertz, electric field distribution is shown here. Now, here we have to identify what is the mode of propagation for cylindrical dielectric resonator antenna. So cylindrical coordinate is basically azimuthal coordinate, radial component coordinate, and Z coordinate. So we have R, phi, Z. R is radial component, phi is azimuthal component, and Z is along Z direction. So radial and azimuthal. But for mode, first we talk about azimuthal. This first is azimuthal variation. Second is radial variation. And this is along Z direction. So when we are saying 1 1 delta, so that means Along the azimuthal direction, number of half-wave variation is 1. Along the radial direction, number of half-wave variation is 1 for HEM11 delta mode. And along z direction, we have the design. The wave is propagating along z direction. Wave propagation AK vector is AZ vector. So again for TM01 delta mode, number of half-wave variation along azimuthal direction, that should be 0. Along radial 1. Similarly for T, transverse electric, transverse magnetic and hybrid electromagnetic. You know what is transverse magnetic. So longitudinal component of magnetic field is 0. So that means SZ is 0. And for transverse electric, EZ is 0. There is no longitudinal component of electric field. It is only in the transverse plate. Electric field will be only in the transverse plate. So that is transverse electric. So and for HEM, EZ is not equal to 0, HZ is not equal to 0. So these fundamental things you know. And for cylindrical system, I told you, the first is indicating the number of half-wave variation along the azimuthal plane, and second is along the radial direction, and third is along the z direction. So this should be clear to you if you want to understand the mode. Okay. So next we have, because this is quad band antenna. So we have seen so far triple band application, triple terahertz frequency. Now, if we alter the structure of the antenna, I mean this would be the second antenna. So if we alter the structure of the antenna, and if we place one tilted, stacked rectangular dielectric slab, so red color is basically cylindrical dielectric slab and blue color is rectangular dielectric slab. Both are made of silicon material. And why we have done this? To achieve the circular polarization using a stacked DRA. So using a stacked DRA also we can achieve circular polarization. So now the structure of the antenna is for the quad band application. It is 145-degree inclined in clockwise direction, rectangular dielectric slab is stacked with the CDR. Dimension is indicated 22 micron by 5 micron by 6 micron. This is the dimension of the rectangular dielectric slab. So now this is giving the CP response, circular polarization response, and also quad band. At quad band it is radiating. So the quad band frequency is 8.79 terahertz, 11.1 terahertz, 13.7 terahertz, and 16.2 terahertz. And impedance bandwidth. So this black color here you can see quad band, 1 band, 2 band, 3 band, and 4 band. This black color is with rectangular slab. So this 4 resonance frequency we are seeing here in terahertz region, and the 10 dB impedance bandwidth is from 8.59 to 9 terahertz. So narrow band 4.6% at the first band. Second band is also narrow band. It is 2.98% impedance bandwidth. Third band is also narrow band, 4.83% impedance bandwidth. And fourth band is also narrow band, 16.8 terahertz impedance bandwidth. So this quad band response we are seeing here. Okay, wait for a second.
I'm changing the tab so that you can see here. This, if you click on stop recording, it will stop. The next screen. Okay. I start recording.
Okay. So the result is basically it is resonating at 8.79 terahertz, second band centered at 11.1 terahertz, third band 13.7 terahertz, and 16.2 terahertz. Now, circular polarization we are talking. It is circularly polarized So for terahertz wireless communication application. So how we know that it is circularly polarized, and
Click on this.
is it left-handed or right-handed?
Then you switch on the screen.
Is it LHCP or RSCP? Left-hand circular polarization or right-handed circularly polarized antenna. So that also we have to infer. So for understanding what is the polarization of this antenna, first we should see axial ratio. The first job should be axial ratio. And after that, electric field vector distribution we will discuss. So first axial ratio we will talk this result. So axial ratio you are seeing here at the quad band, you know what are the quad band frequency it is resonating. So you are seeing it is less than 3 dB. Axial ratio in decibel is less than 3 dB for all the quad band. For all the 4 band, it is less than 3 dB. For all the 4 resonant frequency, that means all the 4 band at all the 4 frequency antenna radiation is circularly polarized. Antenna is circularly, it is having circularly polarized response at all the 4 resonance frequency band. From the axial ratio I am telling, because it is less than 3 dB, you can see in this real, it is clearly shown here. Now, it is circularly polarized is fine. That is from the axial ratio. Now, what is the type of circular polarization? Is it left or right hand? For knowing that, electric field vector distribution is shown. That is the best way. I mean, you just see with when the time progresses, electric field vector, it is rotating in which direction. So for different time in CST Regina studio, you have to see the electric field vectors. And then you can know that, okay, if the time progresses, it is clockwise or counterclockwise, in which direction it is rotating. And then you can say whether it is left hand or right hand circularly polarized antenna. So it is not very tough. So now you see the result, electric field vector distribution on rectangular slab. So XY plane it is talking. The slab is kept in XY plane. So at frequency of 8.79 terahertz, I mean first band. Okay, then second band, third band, and fourth band. For all the 4 band it is so. And time is t is equal to 0 and t is equal to t by 4. A, B, first band, CD is for second band, and similarly for third and fourth band. At all the 4 band, you can know whether it is left hand or right hand circularly polarized antenna. So now you consider the first frequency 8.79 terahertz, and you see it is rotating in clockwise or counterclockwise. So it is rotating in clockwise direction. So clockwise direction means our antenna, proposed antenna at the first frequency, which is 8.79 terahertz, it is left-handed circularly polarized. Left-handed circularly polarized. Similarly, for second band is also LHCP, third band is RSCP, and fourth band is LHCP. That is one method. Other method is also there to know LHCP and RSCP by seeing the 2D far field radiation pattern. So that also I will discuss. So I told the first band is LHCP, then third band and fourth band is also LHCP, and second band is RSCP. So LHCP, RSCP, LHCP, and LHCP. Now you see using the second method, this one. So here far field gain is plotted for phi is equal to 90-degree angle for phi 90. So both LHCP and RSCP polarization is plotted at first frequency 8.79 terahertz. Theta is equal to 0 degree. You have to keep theta 0 and phi 90 degree. So in the CSTS Designer Studio, you can set the angle theta 0 degree, phi 90 degree. And at first frequency 8.79 terahertz. So now from this 2D far field radiation pattern, which power is dominant? I mean, left polarization or right polarization. Which power is high? Which is dominant? That we have to see. So this is here you are seeing -20, here -25, and here it is -10 and -15. This power is more left hand. It is basically left-handed circularly polarized antenna at first frequency. And directly seeing the electric field vector rotation also you can tell whether it is LSCP or RSCP. In fact, this is as per the definition of the left hand or right hand. Electric field is rotating in which direction? Okay. So now axial ratio, I told this is less than 3 dB. What is the bandwidth of the axial ratio? So 3 dB ARBW, axial ratio bandwidth 3 dB. At first band, it is from how much? Bandwidth you can see it is highly narrow band, 1.83%, 6 point, and second is from 10.77 to 11.5. So 6.6 is 3 dB here. So 6.6%, then 3.84%, 3 dB. So 3.84% and 4.8%. So this is the 3 dB axial ratio bandwidth. It is circularly polarized, fine. But what is the frequency range for which it is circularly polarized? That also we should know. So then next is antenna. Again also we can discuss polarization of the antenna, we have discussed in detail. Antenna modes also we have seen. Return loss we have seen. Now next is antenna again. So 1 second.
వాళ్ళకి అసలు స్టూడెంట్ ఎఫర్ట్ 70% పెడితేనే ఇది వాళ్ళు పెట్టరు మనం అంత చెప్పలేం.
Okay, so next we have antenna again in dBi. So we are getting how much gain at the 4 frequency band? 5 dBi at 8.79 terahertz. First band 5 dBi. Second band 4.5. This one 4.5. This is second band 4.5 dBi. 5.5 dBi at 13.7, and at 16.2 terahertz we are getting 6.6 dBi antenna gain. Okay. So antenna gain at terahertz frequency we are getting 5 dB, 4.5 dBi to 6.6 dB. Now I told this is quad band circularly polarized antenna. This is also tunable antenna, graphene tunable. That I didn't discuss so far, graphene tunability, and where we have used graphene material, that also we have to see. So now you are seeing here we have quoted the graphene. Graphene material is quoted here. The graphene material having thickness 0.34 nanometer at T is equal to 300 Kelvin. So using nano fabrication techniques on the cylindrical dielectric resonator, graphene material can be coated. It can be coated. Coating of the graphene material. And what is the purpose of using graphene? So at terahertz frequency, if we tune the chemical potential of the graphene material, if we tune the chemical potential by changing the DC electrostatic voltage, chemical potential will be tuned, and so conductivity will be tuned, it will be changed. and so the response of the antenna can be also reconfigurable. Now, how the conductivity and chemical potential is dependent. So, conductivity formula is shown here. It is function of frequency, resonance frequency. Chemical potential is mu c. So, frequency, second is chemical potential, third is relaxation time, and fourth is temperature. Whether it is 300 Kelvin or 250 Kelvin, 350 Kelvin. So, sigma is highly dependent on temperature also, chemical potential also, frequency also. So this is the formula, Kubo formula for the conductivity of the graphene layer. Now in this figure, bias voltage versus chemical potential is shown. So if you change the bias voltage, how the chemical potential will change? We can change the voltage from 0 to 4 volt, and how the chemical potential is changing, that is shown. And if chemical potential will change, mu c will change, sigma will change. And also, if you change the electrostatic voltage, bias voltage, so the permittivity of the graphene layer, that will also change. Graphene material permittivity will also change, conductivity will also change. Okay, so now after coating, we can see the result. After coating the graphene like this, we can see the result. So here radiation efficiency and S11 is shown. S11 result versus frequency. So how many bands we are seeing? Tri-band, because we didn't stack the rectangular slab. So before that, we are seeing after coating the graphene on the cylindrical resonator. This is the result. Without graphene, black color. At black color result, so triple band it is radiating. And if you change the chemical potential by changing the DC voltage, by applying the electrode at the graphene, metallic electrode. So how this is changing? The S11 is changing for 0.2 electron volt, 0.4, 0.6 and 0.8 electron volt. It is tuning. The frequency band is basically tuning. And radiation efficiency is also changing. So this center frequency pass band center frequency is tuning, and radiation efficiency is also changing. So that means we can change the response of the antenna radiation frequency by changing the chemical potential of the graphene. But after coating the graphene, radiation efficiency is less. Without graphene coating 85% and with graphene coating 70%. So that we have to sacrifice if we are getting the tunable response. Now it is giving tri-band response because only cylindrical dielectric resonator antenna coated with graphene we are discussing. Next, this is the final design. Graphene is again coated here, but you are not seeing because on top it is rectangular slab. So you can see here how graphene is coated, this black color. So now we can discuss the return loss reflection coefficient for the final antenna structure. Without graphene and with different chemical potential 0.2 electron volt to 0.8 electron volt, how antenna return loss response, that we can see here how it is changing. So for different chemical frequency, for different chemical potential, the resonance frequency is shown here. For 0.2 electron volt, it is radiating at quad resonance frequency. Similarly, for 0.4 electron volt, it resonates at different frequency. For 0.6 electron volt and for 0.8 electron volt, it is shown here. Basically, the resonance frequency is tunable. And about the radiation frequency, this radiation efficiency. 89% of radiation efficiency is achieved for antenna without graphene, whereas a maximum of 78% radiation efficiency is achieved with graphene. So that means 11%, how much less? 11% less radiation efficiency. Okay, so it is giving tunable response. You can see here return loss is tuning with chemical potential of the graphene, but radiation efficiency is also reduced. We should discuss both the result. Radiation efficiency also, return loss also. So next is one more question arising, that tunable response is obtained while radiation efficiency is little bit less. What else is there? What about the circular polarization? Is it maintaining the circular polarization after coating with graphene, or so that also we have to see, is it, what is the polarized? Is it linearly polarized, elliptically polarized, or circularly polarized? So now for that, it is below 3 dB. You can see at all the four bands, it is below 3 dB. So the resonance band, it is circularly polarized, and when we are changing the chemical potential, in that case also it is below 3 dB. So the radiating band is, all frequency band, it is less than 3 decibel axial ratio. So that means the antenna is circularly polarized at all the four resonance frequency after coating with graphene. Okay. So, and again, after coating with the graphene, radiation efficiency is less, so again will be also less. So you can see when graphene was not coated, pink color, and when graphene is coated, red, the black, red, and blue and green color result you can see. So gain is little bit less. See, without graphene coating, 6.5 dBi we are obtaining, and after coating with graphene, it is 5.8 dBi only. So 0.7 dBi less. And but it is circularly polarized at all the four bands. Even if when we are changing the chemical potential, we are changing the DC voltage applied to the graphene, it is still circularly polarized. All the four bands is circularly polarized. So we have seen the radiation efficiency, gain, return loss, bandwidth, and circular polarization of the antenna. This is the our proposed antenna results, how it compares with the other reported works, similar works in the literature, that is also shown. So it is published in Silicon Journal, this paper. Okay. So this was the terahertz antenna, quad band circularly polarized graphene tunable terahertz antenna that I was discussing. So next I will discuss terahertz sensor, terahertz observers, and terahertz sensor. Okay. So this work is published in IEEE Transactions on nano biosensor. Okay. So this I will discuss. It is basically ultra thin, ultra narrow bands, dielectric metamaterial absorber for biosensing application. We will see what biosensing we are doing. So now first you see the unit cell of this periodic structure. This is in figure 8 is shown the unit cell. Bottom layer is made of gold sheet, substrate is made of silica. Ionic gel layer is used for doing the electrostatic biasing of the graphene. And this black color circular ring you are seeing, a split ring. You see a split ring because I told metamaterial. So this is made of graphene, circular, a split ring, black color. Ionic gel layer will be on top of the graphene, and this red color, it is silicon, a square split ring, red color. This is also a ring, a square ring, and it is a split ring. So a square, a split ring made of silicon. So silicon, a square, a split ring. And black color is graphene. It is made of graphene, circular, a split ring. So this kind of a structure, if you make this type of unit, say in the CST or HFSS software, if you design the structure like this, what kind of response if the incident signal, the input signal, if the input is, here is the input only, this is the input wave, EX, HY and KZ you are seeing, this is the input signal, incident terahertz signal, incident wave. So then how it will perform? If the incident terahertz wave, it can be incident normally also and obliquely also. Oblique incidence, normal incidence. We will discuss both the cases. So what will happen to the incident terahertz input signal? That we have to see. So what you are seeing is here. The result is discussed here. In the figure B, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 by 3, 3 by 3. Periodic arrangement. Total 9 unit cells are taken. So 3 by 3. Also you can simulate this 3 by 3 and you can take 10 by 10 also. But then processor and RAM size should support 10 by 10. So total 100 elements will be there. If you take 20 by 20, 400 elements you can simulate. But then computer processor and RAM size should support. Okay. So we have done up to this 3 by 3. And here is the result. Figure D. In figure C, all the dimensions are indicated. What is the dimension of the circular graphene split ring? So this circular split ring is there. So what is the dimension of this RGI, inner radius of this ring, the circular ring, outer radius of the circular ring, and a split gap for getting the metamaterial performance. So graphene split gap, GC. And similarly, this red color made of silicon, a square split. So again, what is the split gap? Silicon, this split gap is GS. And what is the thickness? So TD, thickness is TD. And similarly, and what is the this length and width? So LS and WS. So all these things are indicated dimension. And for silica substrate, so length and width, LYW substrate, length and substrate width, all these dimensions are indicated. You have to choose carefully for getting the desired response at your terahertz frequency band. So here it is at 6 terahertz. And so the first band is basically we are getting at 5.98 terahertz, close to 6, 5.98 terahertz. And second is 6.72 terahertz. It is dual band response, concurrent dual band. And what we are seeing for the incident signal, it is absorbing the signal. It is absorbing the input signal, terahertz signal. And what signal it will absorb? 5.98 terahertz, the absorption is nearly 100%, 99.96%. And for 6.72 terahertz, the absorption is 99.8%. This kind of simple structure is giving, nearly perfect absorption, 99.9 and 99.88%. Okay. So it is absorbing the incident terahertz at these two frequencies. So it can be used for a stealth radar application using terahertz band. So now, but we are using for a biosensing application. The reason is this is why we have designed like this. This is ultra narrowband response, you can see. Ultra thin, ultra narrowband, it is written here. Ultra thin, ultra narrowband. Because it is ultra narrowband. The two band is ultra narrowband. So, and this is showing the substrate, gold, silica, then graphene, ionic gel layer is used for doing the DC biasing of the graphene and silicon splitting. Okay. So next we have, what is the bandwidth of this? Ultra narrow band we are telling. So what is the bandwidth of this? So full width half maxima. Full width half maxima at first band is basically how much? 0.017 terahertz. And full width half maxima at second band is 0.015 terahertz. So it is ultra narrow band absorption with narrow absorption spectrum at both the bands with full width half maxima 0.017 and 0.015. Okay, so we will see how it will be useful, this type of ultra narrow response for sensing application. Now here evolution of the observer is shown. Observer 1 is basically only the gold sheet, then gold sheet on top is the silica, then observer 3 is silicon, a square, a split ring, and the final design with graphene circular split ring. So for all the 4 observer in CST, we have seen the reflection coefficient. And we have the reflection coefficient, so we can find the absorption. Formula is here. Basically, absorption is equal to 1 minus reflection coefficient minus transmission coefficient, 1 minus R minus T. Now, transmission coefficient, because the bottom layer is gold metal, gold sheet, so T will be 0, 0 transmittance from the gold sheet for the terahertz incident wave. So the formula is 1 minus R. R is here, reflection coefficient is already plotted here from the CST. So now we can plot the absorption. A is equal to 1 minus R. So absorption for the 4 design is shown here. Observer 4 is the blue color, and blue color we are seeing that this is close to 1. It is close to 1. 1 means 100% absorption. So if we see the result for the observer 4, it is 99.96 and 99.33% at 5.98 terahertz and 6.72 terahertz. And for observer 3, without graphene coating, what is the frequency band? That is also shown in the red color. So frequency band is 6.16 terahertz and 6.84 terahertz, and it is 98% absorption. So without graphene coating, we are seeing it is not close to 100%, it is only 98% without graphene structure. So now with graphene layer, the final observer 4, blue color result, it is close to 99%, 99.96 and 99.43%. Okay, frequency band is 5.98 and 6.72 gigahertz. So next we have, after this, now we have seen some results, the reflection coefficient, absorption, and full width of maxima. So next is how the electromagnetic wave is absorbed, what is the plasmons on the surface for the incident terahertz signal, that also we have to see. So electric field distribution for the observer 3, first you see for observer 3 means without graphene. So with graphene, after coating with graphene, and without graphene, what is the response that we want to see. So observer 3 without graphene coating, electric field and magnetic field distribution is shown, and surface plasmon is shown. So in figure C and figure E, these two figures, electric field and magnetic field distribution is shown. So electric field vectors and magnetic field vectors you can see at the lower band 6.16 terahertz. So at 6.16 terahertz, this electric field encircles the linearly oriented magnetic field. So it is formation of basically magnetic dipole. If electric field is encircling the linearly oriented magnetic field, it is formation of magnetic dipole. Magnetic field is here linearly, and in the at second band, electric field is linearly oriented, and magnetic field is encircling the electric field as per D and F result at 6.84 terahertz. So it is basically the electric dipole formation at 6.84 terahertz. So at first band, electric dipole formation, magnetic dipole formation, and second band it is electric dipole formation. Now after coating with graphene, what is the plasmons, surface plasmons? Without graphene it is shown here, and after coating it is enhanced. The surface plasmons near the graphene you can see the magnitude is high. So basically this is the reason why we are getting close to 99% absorption. In this case it is 98%, after graphene it is 99.96, close to 99% absorption. So that is the benefit, nearly perfect absorption we are getting from the final design. And about the electric and magnetic field, so we can see here magnetic field is linearly distributed at the lower band. So it is magnetic dipole formation, and at the upper band linearly distributed electric field you can see, and then magnetic field is encircling the electric field. So it is formation of electric dipole at the upper frequency band. And surface plasmons is enhanced, absorption is also very high. Now for normal incidence, all this result is for normal incidence. So I was telling that this input signal can be incident obliquely also. Obliquely means theta angle will be changed. So for different theta angle, theta is 0 degree to theta 70 degree oblique incidence, that we have to see the response. You have studied the normal incidence and oblique incidence in electromagnetic field. So that we are doing here now. If theta is equal to 0 degree and theta is shown here, this angle is theta. Theta is 0 means it is normal incidence, you can understand. Now if theta is 20 degree or 40 degree or 50 degree or 70 degree or 80 degree, that is the case of oblique incidence. How it will behave when we change the angle? Incident signal, incident terahertz signal angle, if we change, is it still giving good absorption? That study we have to see, because there is no guarantee that signal will always come in the normal direction. So practically we have to see all the cases. So now you are seeing absorption versus the frequency for different theta oblique incidence. Okay. And in the azimuthal plane, the first result, if you change the phi angle, since the structure is symmetric, so that result will not be affected for TE or TM because of the symmetrical structure. So that is, this result is shown in this figure. For this both kind of incident input signal in the azimuthal plane, the result, this is symmetric, the structure is symmetric. So result will be same, but our concern is basically the incident angle. If theta angle is changed for the input signal oblique incidence, then what will be the absorption? So two figures B and figure C. Figure B is for TE incidence and figure C is for TM incidence, oblique incidence. Now the result I will discuss directly for T and TM. So as per this result shown here, you are seeing the result. 80% limit is here, absorption is 80% here. So up to theta less than 60 degree, theta less than 60 degree. So this dotted pink color, theta is less than 60 degree, we are getting more than 80% absorption. If you go beyond 60 degree, it will be less. So it is more than 80% of absorption of the signal if theta is less than 60 degree for TE incidence. And for TM incidence, it provides absorption greater than 80% up to theta 50 degree, and it provides for upper band, and for lower band absorption greater than 80% up to theta 40 degree. So that means TM is more sensitive, TM incident signal polarization. And for TE incident, it is more than 80% for theta less than 60 degree. For normal incident, it is 99.95% absorption at 5.98 terahertz and 99.88% absorption at 6.72 center frequency of the upper band. So basically close to 100% absorption for normal incidence. And for oblique incidence, it is more than 80% up to theta is 60 degree. So 0 degree to 60 degree. So that oblique incidence result also we have discussed. Next we are seeing this is called parametric analysis, what you are seeing. So parametric analysis, because here we have indicated all the dimension, TDRA, thickness of the silicon, a square split ring is 4 micro, a square split ring gap is 4 micro, LS and WS, which is here, silicon, a square split ring, so 50 micron by 50. How we are getting that? For that study, how we are getting the dimension for the best result? For that study, this parametric analysis is done. So in CST, you can do the parametric study, and optimization option is also there for fine-tune the result. So now for different dimension variations like thickness of silica, the silicon, a square split ring, silicon, a square split ring, and then the next is TD. So TD is a square split ring width, and then we have TS. TS is substrate thickness, thickness of silica, substrate thickness, TS, third one. C, and then D is RGI, RGI is graphene inner radius. RG naught is graphene outer radius. So if we change the dimension, how the absorption will change? So you can plot in origin this color diagram. So silicon square splitting thickness is varying from 2.5 micron to 5 micron. And that you can see 2.5 to 5 in the y-axis, x-axis is frequency changing. And it is observed that absorption coefficient is greater than 95.5% for different values of TDRA for 4 micron. We have to see the best results. For 4 micron, it is 99.99%. So 4 micron is here. This is 4 micron. And red color means perfectly, red means 100%. So 99.99% at 4 micron, if you choose this dimension 4 micron, absorption is 99.9%. At lower and upper band. So lower band and upper band, both are shown here using color diagram. Similarly, we have done for the silica thickness, substrate thickness, graphene inner and outer radius, and the width of the silicon square split ring resonator. Similarly, graphene and radius also. So we have obtained the dimension of the graphene inner radius. How much? For better result, excellent absorption is obtained. So for TS is equal to 2 micron. TS is silica thickness, and RGI is 8 micron, and RG naught is 9.5 micron for good absorption. And for a split gap, for the square split ring and for graphene circular split ring, a split gap GC and GS. So that we have obtained 4 micron and GC is 3 micron. And relaxation time and chemical potential also. So chemical potential we have 0.4 electron volt is giving good absorption coefficient. So all these things we have obtained here using the parametric study for getting the highest value of absorption for our designed structure. So that result we have seen here, we have discussed here. Next is for biosensor application. See, you can, so far we have used for absorber, for terahertz signal absorber, this structure with narrow band, nearly perfect absorption. Now I am discussing the application. The same structure how we can modify for biosensing application. Okay. So how we can use the same structure for biosensing application. Now see, gold sheet is there, bottom layer, then silica substrate, and on top of that we have graphene, circular split ring, ionic gel layer, you know, that is used for doing DC biasing of the graphene. So, and then we have silicon, a square split ring. On top of that we have biosample. Analyte is basically the biosample. What biosample we have taken, that also I will tell. So we have done for cancerous blood cell, cancerous breast cell, cancerous skin tissue, malaria, and for glucose, and for different chemicals. So we have taken as the analyte, and we have done the study for these biosamples. Okay. So full width of maximum, I already told 0.017 and 0.015 from this region. You can measure from the result full width of maxima, so half power bandwidth. And quality factor is coming how much? The observer quality factor in lower and upper band is 351 and 448. So Here the question is what is the formula for the quality factor, for the figure of merit, for the sensitivity, how we are finding this value. So quality factor is peak frequency divided by FWHM, full width of max. Figure of merit, sensitivity divided by full width of maximum. This figure of merit. So that means full width of maxima will be more narrow, figure of merit will be high, sensitivity is high, figure of merit should be high, and that should be the case. High sensitivity, high figure of merit, ultra narrow, less FWHM, high figure. So the formula is S by FWHM, quality factor, all of you know, peak frequency by FWHM. Sensitivity. So two types of sensitivity here we are talking. One is if we change, if we vary the analyte thickness, how much sensitive our proposed sensor is. Second case, which is more important actually, if we change the refractive index of the analyte for different analyte, like malaria, dengue, blood cells, cancerous tissue, different chemicals, glucose. If we change the refractive index, or if we are changing the sample, what will be the sensitivity? What will how much the frequency will vary? Delta F upon delta M. This is very important actually. So two types of sensitivity. The first was for the same sample. If you change the thickness of the analyte, how much sensitivity change? And the second is for different samples, what is the result for the sensitivity? And not only that, at what frequency it is actually resonating. That is even more important. For different analyte, at what frequency it is actually resonating. Because different samples, biosample, will be having different terahertz signature. I hope you got what is happening here. Now we can discuss the results. Okay, so for the study of observer response with varying analyte thickness, means sample is one and we are changing the thickness. So refractive index of analyte we have taken because it is for one sample 1.4. Okay, and then the result we can see here. Proposed observer with analyte on top, frequency response with change in analyte thickness, and third is plot of delta F and sensitivity with change in analyte thickness. So plot of delta F and sensitivity, and the in figure B, frequency response, how it is changing, that is also very important. Dual band, it is dual band. So how the bands are changing for TA 0.1 micron, TA 0.4 micron, TA 2 micron. So how the this blue color is basically for 0.1 micron, and then for 2 this is dotted blue color. So this is how the dual frequency band, how it is shifting, how it is tuning. And now sensitivity, because formula is given here, delta F upon delta TA, figure of merit S by FWH, Q is FP by FWH. So that also we can calculate, and how much it is coming. Sensitivity is 0.5 terahertz per thickness unit and 0.4625 terahertz per thickness unit. So for TA is equal to 1.2 micron. Fine. So next is we will see for different biosamples, for different and full width of maxima and figure of merit is also shown. So using this formula, that also you can calculate how much we are getting, I will tell. So quality factor we are getting 394 and 624, high quality factor for TA is equal to 1.2 micron, and for TA is equal to 2 micron, it is 465. The lower one, fine. So it is about quality factor and sensitivity and figure of merit. Anyway, if FWHM is less and sensitivity is high, figure of merit will be high. So next is refractive index for different biosamples. How the result of this biosensor, terahertz biosensor. So first we designed terahertz absorber, and now it is used for terahertz biosensitive application. So now in this result, what is shown for different refractive index, n is equal to 1, 1.1, 1.2, 1.4, 1.6, 1.8, 1 to 2 we have done. You can do more also, and you can reduce this gap also. You can take 1, 1.05, 1.1, 1.15, 1.2. More thorough study also you can. So then absorption versus frequency result you are seeing. For dual band, because the sensor is dual band. So now for different, because different biosample will be having different refractive index. So at what terahertz frequency it is resonating, that we want to see. And this refractive index belongs to biosample, analyte, okay, of thickness T. Now thickness we will fix. So shows the absorption plot along with performance parameters for varying refractive index with TA is equal to 1.2 micron. So here we have taken 1.2 micron thickness of the analyte, and we are changing the refractive index for the different analyte. We want to see all the regions. So now talk about figure A, absorption versus frequency. So n is equal to 1. This broken red color, it is radiating. This frequency of resonance is lower band is just below 6 terahertz, and upper band is close to 6.75 terahertz. Similarly, we can see the frequency changing, it is varying, where we are changing the refractive index of the analyte. So this much is basically the lower band variation, and here it is the upper band variation. And the second figure, here sensitivity versus the refractive indexes. When the refractive index of the sample is changing, how the sensitivity will change and how the full width half maxima will change. That is FWHM versus refractive index and figure of merit. Figure of merit versus refractive index. In the last, it is quality factor for different refractive index for the lower and upper band in all the cases. So sensitivity we are getting 1 terahertz or 1.9 terahertz and 1.45 terahertz for lower and upper band when n is equal to 1.4. And figure of merit is basically 126 and 100. And quality factor is 470 and 560 for lower band and upper band. So now we have seen sensitivity of the sensor, frequency variation for different refractive index, figure of merit and quality factor. So next we have the sensitivity, full width half maxima, figure of merit and different frequency also, F1, F2 and quality factor for different analyte, for different biosample. If the biosample is a healthy blood tissue, what will be the response? For this type of analyte, healthy blood analyte, it is 1.376 refractive index. For cancerous blood as the biosample, cancerous blood sample, it is 1.39. For healthy breast sample, it is 1.449 refractive index. And cancerous breast sample, it is 1.58. And healthy skin sample, it is 1.84. Cancerous skin biosample, it is 2.04. And for all these cases, we can discuss the sensitivity, FWHM, figure of merit and quality factor. This table is having all the results. And what is the resonance frequency for different refractive index, that already we have plotted here. So more close also we can do. because here you are seeing 1.376, 1.390. So you have to do the more close study. N is equal to 1.05, 1.1, 1.15, 1.20, like that. So for all these cases, when we are changing the refractive index in the CST Design Studio, what result we obtained, that is all. And the sensing performance, when we, yes, this figure is shown for different stage of malaria infection. For different stage, so 1.373 and 1.383 infected RBC have refractive index of this in different stages of malaria infection. So what will be the response of the sensor? For 1.373 and 1.383, how much frequency will shift, at what frequency our sensor will resonate, what is the sensitivity? So sensitivity, you can see this is shown in the table, 0.6772 and 0.5362 for lower and upper band. So lower band was how much? 5.98 terahertz, and upper band was 6.72 terahertz. And quality factor also is shown, 357 and 543. So proposed sensor provides excellent sensing performance for detection of infected red blood cells in different malaria infection stage. Next, for glucose mixed in water for different concentration of glucose, that also we have done. So N is equal to 1.3198 and 1.3594. What is the result for this refractive index? So this was the study for the biosample. Next we have done for the chemical sensing, for different chemical sensing using the same structure.
To understand the digital concepts of logic circuits and
Okay. So for different chemical like ethanol, ethylene glycol, and all these chemicals, glycerin, benzene, sodium chloride, carbon disulfide, vegetable oil, acetone. So refractive index for the different chemicals are shown, and the sensing performance in terms of sensitivity, figure of merit, and quality factor is also shown. So it is suitable for sensing various chemicals shown here. Figure of merit and quality factor is high. So now here is the final result, comparison with other research articles. So here all the results are shown, and for other authors also it is 1, 2, 3, 4, 5, 6, 7 authors we have compared. See, they have also taken number of bands 2, 2, 2, one has taken 3 also. So then these are our results. Quality factor, figure of merit, you can see figure of merit in our case and quality factor in our case. This paper is published in IEEE Transactions on Nanobioscience. This work was done by my PhD student. So now, so far I have discussed about terahertz observers, terahertz dielectric resonator antenna, circularly polarized antenna, and terahertz biosensors. So next, I will discuss. Basically, now I will discuss some hardware for microwave and millimeter wave communication.
యాక్చువల్గా ప్రాబ్లం ఏంటంటే ఆల్మోస్ట్ హీల్ అవుతుంది అన్నప్పుడు కొంచెం వాక్ చేస్తుంటే అది మళ్ళీ
This is for millimeter wave communication. 2i2 MIMO antenna. The first structure. So this is the antenna structure. 2x2 MIMO
ఆల్మోస్ట్ 80%
antenna,
హీల్ అయిన
and all the
తర్వాత
4 ports is
30 hours
indicated here for
నడవచ్చు.
feeding the
నడవచ్చు అని
input
చెప్పారు.
signal.
కొంచెం వాక్ చేయాలంటే కొంచెం ఓవర్ వెయిట్ కదా మ్యామ్, మేబీ అది కూడా ఎఫెక్ట్
And
అయ్యి
front
ఉంటుంది.
structure and
దానివల్ల
back
మళ్ళీ
side structure, how it is actually designed, this 2x2 MIMO antenna, that is shown here.
చాలా కష్టపడి వచ్చాను అసలు.
So keyhole slot loaded circular patch antenna, keyhole slot loaded circular patch antenna. This is the top and bottom view.
చాలా ఎఫెక్ట్ అయింది మాకు.
It is interesting design, and we can discuss the results for this millimeter wave MIMO antenna. So this first result is basically the return loss. Return loss versus frequency from 15 gigahertz to 60 gigahertz is shown here.
అలా ఇంట్లో వేసుకొని ప్రాజెక్ట్ కంప్లీట్ చేయాలి కదా, అదంతా అప్రోచ్ అవ్వాలి. అదన్నా ఉండాలి.
So it is basically radiating at quad band 40.5 gigahertz, 25.6 gigahertz, 34 gigahertz, 29.5 gigahertz, and return loss is minus 41. It is shown here. It is better than 15 dB in all the cases. Bandwidth is also indicated. Narrow band. All 4 bands are narrow band. And then envelope correlation coefficient, diversity gain. So envelope correlation coefficient, it is all less than 0.05, much less than 0.05. Diversity gain was approximately 10 at all frequency operating frequencies, and far field radiation pattern is also shown at 25 gigahertz and 40 gigahertz. 3D radiation pattern, 3D radiation pattern at different frequency. So this is basically for a different port, because this is 2x2 MIMO antenna. So port 1, port 2, port 3 and port 4. Port 1, port 2, port 3 and port 4 at 25.5 gigahertz, and similarly for at 4 ports at 40.5 gigahertz. That is shown here. And 3D far field radiation pattern is also shown at 25.5 gigahertz. How the radiation will look like, in which direction it will radiate. So now some fabricated hardware I will discuss for microwave communication. Terahertz communication we have seen. For microwave communication I will discuss some results. Okay. So here I have designed, I fabricated, this paper is published in Wiley MOTM. Wiley letters, microwave and optical technology letters, MOTL. So here I have designed one voltage controlled oscillator. You can design in Keysight ADS. So transistor I have taken. This is from basically company name is NEC Corporation. NE4210S01. Heterojunction field effect transistor. So heterojunction FET transistor you are seeing, it is visible. It is having 2 source pin. This field effect transistor, heterojunction FET, 2 source pin, 1 gate pin and 1 drain pin. Everybody knows transistor, FET transistor. So 1 gate pin and 1 drain pin and 2 source transistor. We have multi-source pin. Multi-gate is also there for some transistor, but it is 1 gate, 1 drain and 2 source. Heterojunction field effect transistor. Company name is NEC Corporation. Model number is NE4210S01. Everything is indicated here. And how it is connected, that also you can see for designing this voltage controlled oscillator. It is not easy to design and get the performance in hardware for the voltage controlled oscillator at microwave frequency. So active cell, I am calling this one negative resistance cell. Negative resistance cell because BS criteria must be satisfied. Barkhausen criteria for oscillation. That means loop gain, total phase shift should be 360 degree. Loop gain phase angle should be, total should be 360 degree. And the magnitude A beta ideally should be 1, but practically we take 1.05 or mode of A beta is equal to 1.1, so 5 to 10% more to sustain the oscillation, for sustaining the oscillation. So that theory, you know, the negative resistance theory for the oscillation. How we are getting the negative resistance is more important. How we are obtaining the negative resistance, or I mean impedance. So that design I have shown here, I have taken one. This is radial stub. This is known as radial stub. This one. And you will ask for what purpose it is taken. It is a kind of transmission line. And this is the, I mean, radial structure. So this radial stub is taken. This is acting as a bypass capacitor. So LC oscillator, everybody knows. For this high frequency oscillator, so LC oscillator we can design. So this is acting as C capacitor, and then where is L? L and C in parallel. So L is here. This is L. This is acting as L. This one. So here I have done this. This is called via ground. This is acting as inductor. This thinner transmission line. So and this is grounded via ground. So for that also you have to drill a hole via hole. Otherwise, how you will ground? Because it is high frequency, microwave frequency. So now L and C in parallel and then ground. LC resonator for getting the negative resistance. This is the concept used here. And then you will ask for what purpose these two we have used. So this is for biasing. We have to bias the transistor also. Operating point, operating bias point. So input side and out, drain biasing and gate biasing, gate pin and drain pin. So this is bias network. How you bias the transistor? You need one inductor. You can use resistor inductor also, and then in shunt there will be capacitor. This is what I have done here. So then biasing is also done. Negative resistance already I told you the concept. LC, this is called LC oscillator. And we have to check whether we are really getting negative resistance or not. So how we will check? Calculate the input impedance here and check the real part is negative or not. If it is not negative, it will not oscillate. You will not get any oscillation signal. And if everything is good, you will see the peak like this. You can see the response. I have taken from how much? A start frequency is 1 kilohertz. A stop frequency is 3 gigahertz. And from 1 kilohertz to 3 gigahertz, there is one peak. Clearly you can see there is one peak. Correct or not? And power is also very good, 4.25 dBm. And this frequency is 2.5696 gigahertz. This is hardware result I am saying. This is not the simulation. This result is all hardware results on here. So now I will discuss more. I have discussed only about the biasing circuit at negative resistance cell, biasing circuit and negative cell. Next is the resonator design. Resonator also we have to do. So resonator you can see this is basically made of one transmission line incorporated with varactor diode. because we are designing voltage controlled oscillator. So tunable response we want, change the voltage and it will give you different signals. Output signal will vary. You will get different RF signal. So then variegated diode, where I have connected, you can see here this black color is there, a small one, very small one. This is the variegated diode. It is teeny. So you have to solder very carefully. And here also it is via ground. This hardware you are seeing here, this is one via ground is here. If you don't do properly, real will not. Here also this is via ground. Because this anode and cathode pin is there. Variegated diode will be in reverse bias, everybody knows. So anode, here I am giving the voltage 0 to 15 volt to the anode. So cathode, reverse bias. So cathode is then 0. Then it will be reverse bias. Okay. Cathode should be anode and cathode. Cathode should be more voltage, na? So cathode is this one. This is the cathode, and here it will be anode. Then it will be reverse bias. Okay. So that PN junction variegated diode, you know. So carefully anode and cathode you have to do. If you do the opposite, there will not be any result. Then no result will come. So this proper, you have to see, is it reverse bias or not. So this cathode pin, we are giving 0 to 15 volt and anode is here grounded. So next is, here I have done this transmission line, microstrip line. Microstrip line having some width and length, correct? What should be the width, what should be length? Length is very important for your frequency because it is designed for what, 2.26 to 2.80 gigahertz. You can design for Wi-Fi application also, that also I have done. 5.8 gigahertz, 5.2 to 5.8 gigahertz. But then you have to very carefully choose the, dimension, design dimension. You have to choose the electrical length of this and what is the impedance of this microstrip line. So what is the width of this line? And here series capacitor 2 picofarad is taken. So microstrip line in series with the capacitor and their variegated diode I have used. Variegated diode I didn't discuss about the variegator, which variegator I have taken. So it is SMV 1232079LF. SMV 1232079LF. It is company name is Skyworks. So what is the variegator capacitance range? That is from 0.72 picofarad to 4.15 picofarad. You can take another one also. Another model is SMV1231, SMV1234. So as per your application, you can design. You can choose the different variegator. I have taken this one. And then this you are seeing for reverse biasing of the variegator. This L and C, this is shunt capacitance, and this is acting like inductor, choke. So that we have used, and 0 to 15 volt for this variegator bias voltage, reverse voltage we are giving. This was the design of variegator incorporated resonator for the VC. The last part is basically output matching network. Wait for a second. So next we have now the last part, this output matching network of VCO. So we have taken single stub microstrip line with single stub. All dimensions, everything is indicated here. Impedance of the line I have taken 50 ohm. And finally the output port. Now result, if you want to discuss for this, for the proposed, yes, here is the result. Here is the hardware result for this VCO. Substrate is shown here. Nil-Tech substrate. Epsilon R is 3.2, loss tangent 0.0025, and thickness is 62 milli-inch. 62 milli-inch is equal to 1.524 millimeter. This is the hardware result of the fabricated prototype. At 2.5696 gigahertz, we are getting the output power from here. This is output port, SMA connector. So we are getting 4.25 dBm output power at 2.56. Clear peak we are seeing. And this is VCO, so we have to see the oscillation frequency is here, output power is here, and also the phase noise. Phase noise also we have to see. So phase noise is how much we have got. Phase noise is minus 115 to minus 155 dBc per hertz at an offset from the carrier 6.5 megahertz. At an offset of 6.5 megahertz from the carrier. Carrier frequency is here. This is the carrier frequency. So from the carrier frequency, if you take offset of 6.5 megahertz, the phase noise for different voltage, because this is VCO, that value is minus 115 to minus 155. So here is the carrier frequency. One carrier is here at an offset of 6.5 megahertz I have measured. Okay, you are seeing this offset. So here also some power you can measure after changing the cursor, and then you can calculate what is the phase voltage. Or that is using the equation formula. Other method is some spectrum analyzer directly will give you phase voltage versus the frequency. Some spectrum analyzer from the Rode and Schwarz R&S. So it will plot phase noise versus frequency. For different voltage, you can measure the phase noise. Okay, so and harmonic suppression. First harmonic suppression. It is resonating at 2.5696. So first harmonic will be into 2. This fundamental frequency F0 into 2F0. So at 2F0, you will see a peak. But that peak will be suppressed by how much? More than 16 dB. That peak will be, harmonic will be suppressed by 16 dB as per the hardware result which I obtained, I am saying. This is my result. And then temperature study also I did for this designed VCO. If we change the surrounding temperature for the circuit, active circuit, what will be the response? That also we have done. Because actually I used this component for wireless temperature and pressure, wireless pressure and temperature monitoring. So this study also I did per degree Celsius. Up to 80 degrees Celsius it was working as per the specs of the transistor. Transistor and diode should work, otherwise how it will work? So you have to choose accordingly. And then output power versus the different vector voltage is shown here. Output power versus different vector voltage. Reverse bias voltage. So how the power is changing, that I have shown here. Maximum we are obtaining 6.5 dB power. At what frequency we are obtaining? So this frequency we are obtaining. This frequency is corresponding to basically 2.75 gigahertz. So you are seeing initially for the vector voltage 0 volt, 1 volt up to this one 7 volt. This is almost linear response, and then it is non-linear response. So that is because of how the vector capacitance is changing with respect to the reverse voltage. If you plot the capacitance of the vector diode versus the applied reverse voltage, so that will be also non-linear. Initially some voltage it will show, I mean, close to linear and then non-linear. So this is why this type of result we are getting, and we are getting 2.26 to 2.80 gigahertz is the tuning bandwidth, 2.26 to 2.80 gigahertz. So total 540 megahertz tuning bandwidth. You can obtain the signal with frequency ranging from 2.26 to 2.8 gigahertz using this circuit by changing the vector voltage. Okay, so I have discussed today about terahertz antenna, terahertz observer, terahertz sensor, and then voltage controlled oscillator. Now, here this one you are seeing hardware for the antenna, fabricated hardware, but this is broadband antenna. This is a broadband antenna for our application. So, this is basically the top and bottom. Both I have done. Defected ground structure, it is based on DGS. Ground plane, I have done the patterning. There is some pattern. This pattern is hexagonal slot. Hexagonal slot is used for getting broadband response on bottom layer. On top layer, coupled mindered, this one. So this is coupled mindered, a stepped impedance resonator structure. Mindering also I have done. You can see the mindering here. And this coupling between two SIR is also done here. So the name is coupled mindered SIR structure. And it is incorporated with the microstrip feed. This is the microstrip feed to achieve a filtering response. So it is filtered filtering antenna. It is broadband also because of the hexagonal slot in the bottom layer. So substrate I have used the same substrate, this one, which is given here. All the details on here. So now the result. So antenna return loss is shown here, simulated and measured. Red color is measured. So you can see the bandwidth, it is broadband antenna. 62% is the fractional bandwidth. 62% we are getting. So 2 to 3.8 gigahertz measured bandwidth. So another important thing is the measured antenna again and the radiation pattern. So both the simulation and hardware radiation pattern is shown here in an anechoic chamber. So in an anechoic chamber we have done this measurement. You can see how the results are, simulation and measurement. And this is as per this result, you can infer that it is a bidirectional radiator, correct or no? It is a bidirectional radiator, and this type of mindering SIR was used to reject the band from 4.6 to 5.25 gigahertz. So 2 to 3.8 gigahertz it is radiating, and 4.6 to 5.25 it is rejecting. Antenna gain is measured gain is 3.4 dBi, because measured gain is mainly important, how much we are actually getting. And this I designed for the wireless sensor application. Okay. And this is basically the 3D plot is on here, how it is radiating. Both sides it is a bidirectional radiator. So if you have any question, you can ask. I have more to discuss, so many things are there. If you tell, I will continue. This is low noise amplifier with hardware. This is also very interesting thing. So you can ask if you have any question. Yes, Kalpana madam.
Sir.
Yes, yes.
Participants, if you are having any questions, please ask. Sir is asking you to respond. Sir is asking you to respond, please.
You can send message also, no issue.
Sir, one question is in chat box, sir.
Okay. What hardware equipment you have used, sir? Okay, we need for lab establishment. Fine. Okay. So basically, if you want to establish lab in your university, so I will give you all the contacts. So first, basically, you should have simulation tool, key site areas for low noise amplifier design, voltage controlled oscillator, active and passive circuits. For antenna, you can have a CST Design Studio and HFSS. This was about software tool. And for terahertz photonics, you can use console multiphysics. And this one, the CST also you can use. CST, HFSS also you can use. And for hardware, so in NIT Warangal, we have in our CRIF center, you can also use the facility. It is open for everyone on payment basis. So we have fully automatic hardware fabrication prototyping machine. So you can fabricate your hardware antenna here. Any hardware, filter, amplifier, coupler, divider, phase shifter, antenna in NIT Warangal. So here the payment will be on the basis of what is the width and the length of your substrate, like you are seeing here. And you want to print single side, like this, it is single side printing. Or here I have printed, this is also single side. Here I have printed both sides. So if you print both sides like this, double payment. So if it is single side 1,000 rupees, then 2,000 rupees. So I must tell you the rule here. And if you want to establish the facility there, so you can get one fully automatic PCB fabrication machine. And then for this return loss measurement, I mean a scattering matrix measurement. For S matrix, you can get a vector network analyzer. So in Warangal, we have up to 44 gigahertz. Up to 44 gigahertz facility we have here. So that you can use. That measurement facility also you can use. Fabrication facility you can use, measurement also on payment basis you can use. And for a spectrum analyzer, because this result is not VNA result. This is called a spectrum analyzer, this hardware. Written portable analyzer. This also we have in Warangal, portable analyzer, up to 44 gigahertz. So this also you can get, this is basically Keysight company. You can get from R&S or Keysight or NSU. So that is as per the quotation you can. And a spectrum analyzer and vector network analyzer. So VNA. This result is from VNA. This one, noise figure and gain. Both noise figure and gain we obtained in vector network analyzer. This amplifier gain and amplifier LNA noise figure. So for that you need one VNA. 2-port VNA is cheaper. 4-port VNA will be expensive, and the frequency range will matter. Up to what frequency range? Many companies are supplying. So a spectrum analyzer you can get, VNA you can get, and then a quick chamber is required for this measurement. Here, this one. All these three, 1, 2, 3. This is all hardware results on here measured. So you need an anechoic chamber. Antenna gain you will measure in an anechoic chamber. Antenna radiation pattern also you will measure in an anechoic chamber. So that Intupal company and Mori Microwave is there. Many companies are there actually. So they will help. Any contact you need, you just let me know. Okay. So all this facility we have here. Anechoic chamber also we have in NIT Warangal. That also you can use all the facility. Up to 44 gigahertz we have all the facility. Yes, any other question?
Excuse me, sir.
Yes.
Sir, myself is Santosh from Sahe, sir. Actually, I want to know just a little bit information about 3D printer, sir, which you are using.
3D printer we have for ceramic. Cost is very less. It is 1.5 lakh rupees. If you want metal 3D printer, that also we have in NIT Warangal. You can use on payment basis. The cost is 1 crore.
Okay.
So metal also we have. And ceramic also we have. So I told now all the facility we have in central research instrumentation facility. Any help you need, you let me know. You can use metallic, 3D printer and ceramic also for the design.
Okay, sir.
So you contact me for any help, okay?
Sir, can I get, sir, your mail ID or something like that?
Yes,
sir?
yes. My email ID and phone number both. You can note down. I
So
am
I can
messaging
contact
in.
with the institute website, na, sir?
I will send you the link. Yes, yes.
Okay.
So check the this chat box. I am sending my email ID and mobile number. Okay. Yes, check the chat box. Okay. Any other question? Kalpana madam,
Esther.
we can conclude.
Yeah, can you come at 2 o'clock, sir? I mean,
Yes, yes, madam. Sure, sure.
Okay, sir. Okay, sir.
Thank you, sir, for wonderful
Thank you. Thank you very much.
Okay, sir. Okay, sir. Let us meet at 2 o'clock.
Okay, okay.
Sir, one more question in the chat box, sir.
Another question is
Please.
there in the chat box.
Working between 70 gigahertz to 500 gigahertz. So for this millimeter and terahertz frequency range, I mean 0.5 terahertz. Basically 70 gigahertz to 100 gigahertz millimeter wave, and then we have terahertz after 100 gigahertz. So this facility, if you want to use, IIT Delhi is having up to 1000 gigahertz. IIT Roorkee is also having up to 1000 gigahertz. So if you want any support, so let me know. This is also possible. Okay. I mean hardware fabrication I am taking, fabrication and measurement. Okay, thank you. Thank you very much. Madam, we can conclude.
Sir.
Okay, sir.